first thing to know is that for modern stratigraphy, the base or the anchor of the time chart is the GPTS, the Global Polarity Timescale. So let's talk about Polarity Timescale and about paleomagnetism. And you're probably aware that the Earth has a magnetic field and that this magnetic field changes periodically. It's not regular, but it changes. It goes from normal polarity to reverse polarity. And actually, this is something very useful that can be used because if you look at mid-ocean ridges, you know that new basalt is formed at the mid-ocean ridges, and that is the cause or the root mechanism for continental drift. But what's more interesting perhaps for stratigraphy is that this basalt, as they form, will essentially capture the magnetic polarity of the time of formation. And in fact, this is how tectonic drift was proven. It was by looking at the polarity of the bands of basalt away from the mid-ocean ridge that showed that they are moving equally in both directions away from the ridge. And that was really the proof in the pudding, if you want, for the fact that continental spreading was happening. But a corollary of this is that you now have a record of basalt that have a polarity record, so positive or negative compared to the present, and that gives you those beautiful, or is represented by these beautiful black and white lines that you see below, the magnetization. So why is this significant? Well, it's significant because paleomagnetism can be applied to a wide range of material, including sediments. But it's also significant because the basalt in which we have this record can easily be dated using absolute dating methods. So here we have an opportunity to have an absolute age to calibrate the GPTS. And by extension, if we have a calibrated GPTS and we can calibrate other sediments and biostratigraphy to this GPTS, we have an absolute age for our timescale, an absolute timescale, which is really a goal for stratigraphy. So how does radioactive decay work? How can we date rocks using radioactive decay? It's a fairly simple process. If you imagine that you have a rock that contains, in this case, uranium, which is a non-stable or radiogenic isotope, that isotope will have a half-life. So what is a half-life? A half-life is the time required for 1/2 of the original mass of the isotope to undergo radioactive decay, so to transform into another daughter species. In the case of this particular rock, we can say that at t equals 0, when it forms, so you have 0 half-lives, the rock is a crystalline rock with only uranium. But of course, with time, this uranium will decay into lead, which is the daughter product. And at t equals 1 half-life, you will have half uranium, half lead. And then at t equals 2 half-life, you will have only 1/4 of uranium left and 3/4 of lead. And of course, and so forth and so on, every half-life you half the amount of the parent isotopes and you obtain a daughter isotope. In the case of uranium-lead, uranium is the parent and lead is the daughter. But if you know the radioactive constant for your system, so for uranium-lead, for instance, if you know the constant, you can determine what the half-life time should be, and you can then use this as a radiometric clock. So in this example here, you can see the principle is fairly simple. The more daughter isotopes you have, the older the rock must be. And if you know the decay constant, you can determine that age with great accuracy. There are, however, some limitations to radioactive dating. First of all, these elements are usually in trace amounts, so their measurement is quite difficult. You have to be very precise in your measurement. So that's challenge number one. Challenge number two is that these elements can actually move. So if you have a closed system, a mineral that does not change over time, that's great. But if you have weathering, metamorphism, diagenetic transformation, you could actually reset the clock and thus have an age that is not accurate. And because they're found in trace amounts, they're very difficult to apply to things like sediments, for instance. Some sediments are very hard to measure or to determine using absolute methods. So these are all limitations of radiometric dating, which is why it's so exciting to be able to apply this to the basalts, where we have a GPTS record, a global polarity record for paleomagnetism. And this is what Kendi and Kent did in 1995. They looked at the polarity record, and they used, here you have the blue arrows, they used some of those basalt to do absolute dating. And with the absolute dating, they then could do some simple linear interpolation, assuming that the spreading rate was constant, and they came up with an absolute age for the different crons, or the polarity crons, that they have uncovered. So here you have the last 5 million years of crons. So you have the Gilbert, Gauss, Matuyama, and Bruns crons, and on the left you have the age, the absolute dating of these crons. And now you can see how having this record of absolute dating of the seafloor can be useful, because you can use the law of superposition, and if you know the age of the basalt, you also know the age of the very sediment on top of that basalt, the very first sediments that were deposited. And if you have key species appearing, for instance, in those deep sea sediments right on top of a well-dated basalt, that gives you an absolute age for that species as well, or at least a good bracketing of that age. So that's how modern stratigraphy comes up with timescale. You have an absolute dating of the reversal of the polarity timescale based on the MORBS, or the mid-ocean ridge basalt, and then everything else is deducted through the law of superposition, but also by dating different events and looking in between these events. If you find one new event, you can deduct what the age of that event would be. So it's a combination of absolute dating and relative dating that gives rise to the absolute timescale that we have. And nowadays, more often than not, dating is done to some extent by orbital tuning. So orbital tuning plays a big role in this story of building a modern timescale for the geological time record.